Imagine that you wanted to take a spaceship and fly it directly from Earth to Mars. This might seem fairly simple, going from one planet to another, kind of like hitting a golf ball directly into a cup. However, this is actually very difficult because this picture of just two planets is way oversimplified. First off, in the solar system, there is a lot of objects and they're all moving. So even that's going to make it more difficult to travel from one planet to the next. And also when we're looking at this path, how far away is that? Well, let's use the golf ball analogy here. A golf cup is 5.4 centimeters in radius. Mars is about 3.4 times 10 to the 6 meters. So now let's put in the real distance between Earth and Mars. It varies, but has an average of 2.25 times 10 to the 11 meters. If we're going to use that same scale to a golf green, the golf ball and the golf cup would be 3.6 kilometers away. That's a pretty tough golf shot to make. And what makes it even more difficult is we have to introduce the gravitational fields. First off, the largest one from the sun here is pulling everything towards it. But then we also have the gravitational field of Mercury, Venus, the Earth, and of course of Mars. So in this picture, all these colors are showing the fields or the pull that's occurring from different directions at different angles from objects that are moving. So space travel, definitely very difficult and takes a lot of calculations and understanding of just a bunch of different stuff. And it's scenarios like this that we're just going to start to understand by looking at maybe 2 or 3 planets and how there can be multiple gravitational forces. So let's take a look at multiple gravitational forces. All right, so to calculate multiple gravitational forces, we first have to start with calculating gravitational force. Unfortunately, we did this in the last lesson. We calculated between 2 planets, and we said the force between 2 masses is going to be Fg is equal to Gm1 m2 over r squared. Those masses represented the masses of the planets, and the radius represented the distance in between those planets or those masses. Okay, so to look at multiple gravitational forces, we're going to have 2 masses here, let's say the sun and the Earth, and we're going to throw the moon in between these 2 masses. This would be the position of a new moon, where the moon is going to get pulled by the sun's gravitational field that way, by the Earth's gravitational field this way. So there's gravitational force to the sun and gravitational force to the Earth, because the sun's going to pull the moon towards it, but the Earth's also going to pull the moon towards it. So let's see which is going to be stronger and what's going to happen to the moon. So we're going to use that formula from before. Fg is equal to Gm1 m2 over r squared. This is calculate the gravitational force of just one of those things. So either the sun pulling on the moon, and then we'll have to do it again for the Earth pulling on the moon. So this one here is going to be the force between the sun and the moon. We can see that m there is kind of yellowish like the sun, and the other one's gray, kind of like the moon. So plugging our values are usually on a data sheet. The gravitational constant, again, 6.67 times 10 to the negative 11. That's the same for all gravitational force questions like this. Then I put in the mass of the sun. It's a really heavy object. It's 1.99 times 10 to the 30 kilograms. It's almost unimaginably big. We put that in, and then the moon's still very big, 7.35 times 10 to the 22, but way smaller than the sun. The challenge for this question, I think, is the radius. The radius is from the center of the sun to the center of the moon, but that's usually nowhere on your data sheet. So looking on this picture, how can we find the distance between the moon and the sun? We have to look at other distances that it gives us. So first let's start with, well, we know the distance from the Earth to the moon is 3.85 times 10 to the 8 meters. That's the moon's orbital radius on your data sheet. Okay, what else do we have? We also have the distance from the sun to the Earth, because that's the Earth's orbital radius, Earth's orbiting around the sun. And that's 1.5 times 10 to the 11. So looking at these 2 distances, we can use them to figure out, well, if we know the distance sun to Earth and moon to Earth, we can just subtract. So I'm going to take this 1.5 times 10 to the 11 minus the 3.85 times 10 to the 8, and we'll get 1.496, whole bunch of decimals there, times 10 to the 11. So actually pretty much the same distance of the sun to the Earth as the sun to the moon, because the Earth and the moon relatively are very close to each other compared to the distance of the sun. So just 1.496 times 10 to the 11 our distance from the sun to the moon. But it is a difference, so let's throw it in there for r and make sure we square that value. we get a gravitational force from the sun. The sun is pulling with 4.358 times 10 to the 20 newtons. A pretty big amount of force, but these are some pretty big masses. Next, let's take a look at the Earth. Okay, so I've put the force from the sun there. Now we'll calculate the force from the Earth. So now I've changed the mass. That blue mass there with the green outline is supposed to represent the Earth, but I've kept the moon the same. This is the force between the Earth and the moon. So how much is the Earth pulling on the moon? Okay, we're going to plug in our masses. Now we have the same gravitational constant, 6.67 times 10 to the negative 11. And then we have 5.97 times 10 to the 24. That's the Earth's mass. And the same 3.5 times 10 to the 22, the same mass that we had of the moon in the last example, because we're still looking at the pull on the moon. R squared is a bit easier here because we have 3.85 times 10 to the 8. We're just going to put that number in, square it, and we get an answer of 1.974 times 10 to the 20 newtons. So now that we calculated our two forces, let's look at what overall is happening to the moon. We're going to get rid of that math and show the two forces here. The sun is pulling this way with 4.358 times 10 to the 20, and the Earth is pulling this way at 1.974 times 10 to the 20 newtons. So if I was going to look at the overall force, I'm going to add these two forces together. But when I look at this, I'm not going to add those two numbers together because there's something different about them. They're pointing in different directions. The sun's going that way, the Earth's pulling this way. So I have to assign one of them positive and the other one negative before I add them together. So I'm going to choose to make the sun's, let's put this in kind of orange, negative. I'm going to call to the left on my picture negative and to the right positive. So now I'm going to add those two forces together to find the overall force pulling left and then pulling right. And I get an answer of negative, or to the left on the screen here, 2.38 times 10 to the 20 newtons. So that's how we handle multiple gravitational forces. You calculate the force one way, the force the other way, or even if the forces are in the same direction, find what the forces are and then add them together. But make sure to put in signs to keep track of direction if they're going the same way or opposite. And that's really all we have in this lesson. But just before we leave it, let's take a look at this number. 2.38 times 10 to the 20 stronger towards the sun. The sun is pulling on the moon more than the Earth. Why does the moon orbit the Earth? If the sun's pulling on it more, it seems like the moon should be orbiting the sun. Maybe it should look something like this, the moon going around the sun, because it's pulling the most on it. Well, it actually is orbiting the sun. The moon is orbiting the sun, but while it's orbiting the sun, it actually just happens to be orbiting the Earth as well. So kind of interesting, the sun's actually pulling more on more on the moon than the Earth is, but it just happens to be orbiting the Earth while it's orbiting the sun. All right, so that's all we have for the lesson today. Kind of a quick one. I hope that helped you to understand multiple gravitational forces, or what's called gravitational vectors as well. Thank you so much for watching, and I will see you in the next video.